G'day and thanks for joining me. Okay, so there's a big concept and a simple little rule implicit in this question. So the big concept is fields and what fields are and what they're not. We'll get to that in a moment. The second one is being able to apply simple rules. We've got a grip rule and a push rule. The right-hand push rule, we'll use that a lot, along with the grip rule in year 12. That's why it's really important to sort of get these and nail them and get them right. So the right-hand grip rule, you have to use your right hand. If you're left-handed, you still have to use your right hand because the laws of physics haven't flipped. Okay, so the right-hand grip rule is your thumb points in the direction that the conventional charges or the positive charges are moving, which is down the page for the wire on the left, and then your fingers grip and then they go around in these concentric circles showing where the field is coming. And so the field, because of the wire on the left, is coming out of the page. But we also got this wire on the right. Very tempting to grab that wire and then go, oh, what's going on here? That's why it pays to use your reading time well and look for things like this. This is what reading time should be focused on, reading the questions carefully and looking for these things. There's no current in the right-hand wire at the moment, and so there's no field, and so really the only result is the one that's coming out of the page. But if you did grip that right-hand wire before you kind of worked out what was going on, that's probably giving you a bit of a clue to this second part of this question, which says what happens as we increase the current I2 from 0 all the way up to twice what the I1 current is. So you can imagine there'll be a midpoint there where the two currents are equal, in which case the right-hand grip rule would show from the wire on the left that the field line's pointing out of the page, and the right-hand grip rule applied to the wire on the right shows that the field lines are pointing into the page. And at that point, we should realize that there's zero net field. Now, it's not because the field lines are going here and the field lines are going there and the field lines cancel out or any of the other black magic that I've kind of seen written about this. Fields don't interact with fields. Fields are regions of space where an object with the appropriate property experiences a force. The gravitational field is a region of space where an object with mass experiences a force. In these magnetic field lines, it's an object with ferromagnetism that's going to experience a force. And we have an imaginary, and they are imaginary, test north pole that we could kind of put there and go, which direction would a north pole experience a force because of this magnetic field from the wire. And so if we put our imaginary test north in between the wire, it's going to experience a force into the page and an equal but opposite force out of the page. Those two forces on that test object are what cancels. That's why there's zero field in the middle. All right, so then that gives us a few options. It pretty much rules out B and D. It leaves us with C. Well, if the field lines are one direction above the line and they get to zero, then as the I2 current increases, the change is going to be in the same direction, which leaves us with A.